Okay, so in the last class, we talked about drift current specifically. We started with drift current due to hole transport and then drift current due to electron transport. And we noticed that for an applied electric field, electrons and holes will flow in a direction that the currents will add up. For both carriers, both types of carriers, the total current will be the sum of the individual current components, right? So this was the take-home message from our discussion about the drift current for carriers in general. Just a quick recap. N represented the number of electrons, P represented the number of holes. By the way, when I say number of electrons and number of holes, these are electrons and holes available for conduction. Okay, not, if there is an electron which is stuck in the valence band, say, that's not it. It's only the electrons that are available in the conduction band. Okay, what was E? E was applied electric field. The lowercase e is the charge of an electron. And interestingly, mu n and mu p were two constants that we basically thought of for this. We noticed that when you apply an electric field, the velocity of the charged particle is somewhat proportional to the electric field, and there is a catch, and I told you that I'll change that narrative today. The initial narrative was, as you increase the electric field, the velocity of the charge goes up almost linearly. And we thought of writing a linear equation like y equals mx, and instead of y equals mx, you have v equals a constant times c, that constant being mu, right? And for electron, we started using mu n. For holes, we started using mu p. That was the story at the time, right? And I told you that, yeah, this linear relationship will change somewhat, and we'll see that in the class today. Now, keeping that simplistic idea in mind, this is the equation that we arrived at, where the total drift current density, remember, this is current density. Current density is nothing but current per unit area. If you multiply this with the cross-sectional area through which the current is flowing, you get the total current. Remember that. Okay, so let's move on to the next one. We also looked at this simple math problem, but we kind of rushed it a little bit. So I'm going to go over this one more time to make sure you are all on the same page. So consider a gallium arsenide sample at 300 Kelvin temperature with doping concentration Na and Nd with some numbers. Don't worry about the numbers now. So let's see what's given. Let me just use a different color because the red markups are already there. So we have Na and Nd. We have the temperature. We know what material it is. So gallium arsenide. Calculate the drift current density if the applied electric field is this much. Okay, so drift current density, as you've just seen, is the sum of the two components of electron drift and hole drift current. We already know the electric field. We know the charge of an electron. We know the electric field. We know the charge of an electron. We know mu n and mu p. How? Because we know the material is gallium arsenide, and there is a chart that will be given in your exam or any other things where you could basically see the values of mu n and mu p for a certain material. Okay, so you know this already. These are constant. These are experimentally measured. Okay, what else is missing? The only thing that's missing now is number of free electrons and number of free holes. And this was the equation that we saw in the previous lecture, which basically talked about the compensated semiconductor, where you have both types of doping concentration, Na and Nd, acceptors and donors. So you just put in those numbers. Here, the math question was simple because one of them was 0, but imagine it, there was a number, say 10 raised to 15. Doesn't matter. You can still use the same equation, put in those numbers, and get the number of free electrons there. Okay. All right, and by the way, there was one other thing, intrinsic carrier concentration. Remember, there was another chart where we saw the intrinsic carrier concentration for silicon, gallium arsenide, germanium, and other materials in one of the previous lectures. Don't worry, in your actual exam, midterm or final, I'll give you a page of chart. You don't have to create a cheat sheet from by yourself because it's too much work. I'll give you those numbers. Oh, you just have to go and look at the numbers and put it back in. That's all. So why are we giving you these numbers? Because they have to be experimentally measured. I mean, there's no formula that will give you those numbers otherwise. Okay, so you have to just look it up. Okay, now once you get in, you could also use a similar equation for P and do the whole calculation. Or remember, there was a simple relation. The N times P equals Ni squared for semiconductors. Number of electrons times number of holes will always be equals to intrinsic carrier concentration squared. So once you calculate n, you can easily calculate p using this simple formulation instead of going through the math again. So you know everything now, just put it back in and you know the drift current concentration. So these simple math problems are there to just help solidify the usage of this equation. But I hope you somehow know in the back of your head the origin of these equations. And this is the principle, basically. Even if I make you derive the equations from scratch, which will be good for the time, but after a couple of months or so, you'll forget, right? After you're done with this semester, you move on to the next semester, everything will be gone, right? So why bother going through the pain when you don't need it? But it is necessary for you to know, at least in bits and pieces, where it comes from, so that at some point in your life, if you ever need to know the origin, or if you ever need to go through the steps, you can go back and look it up. Okay, so you have to know that this is how it comes. This is the process how we could calculate. Maybe you don't need to go through the calculation. Done. Some calculations, you get to the end of it, but you need to know it doesn't just come out of thin air. Okay. All right. Interestingly, when I was a student, for most of these equations that you see, I had to go through the steps. Basically, there was a lot of emphasis on math. We basically derived many of these equations. Even the chronic penny model, for example, the one that I hopped through, like this is an equation, this is an equation, this is an equation. I just kept putting in equations there. But we had to go through it. That was good, obviously. That opened up the, I think that really solidified the baseline. But in the end, I forgot all the steps. So even if I start today, it's as if I never saw it. So I'll have to start from the scratch. But the good thing is I have pointers. I know where it came from, so I could go back and redo it. Okay, and one more reason, we are living in a modern age where we have a lot of simulators. We have a lot of computing tools. You don't necessarily need to solve differential equations by hand anymore, right? You have Mathematica, you have many other tools. Just put that equation in, it will solve it. So when you have tools like this, and you are an engineer whose job is to solve problems in the circuit system level. So maybe you don't necessarily need to spend time, going through all those steps. That's the ideology. But remember, somebody has to do that. Otherwise, nobody will know. Okay, getting back to the discussion again. This is a very simple slide, but this has some implication, which I want to highlight. Conductivity and resistivity of semiconductors. So let's first look at the figure on the left. This is a very common, and I hope you have seen that in the high school physics courses, very common figure, which you use to represent the resistivity of metals or metallic materials. Imagine you have a chunk of metal with cross-sectional area A and length L. Okay? What is the resistivity of that metal? Can anybody tell me? The resistance of the metal is resistivity times length over cross-sectional area. Resistivity is the material level constant. So copper has a certain resistivity. You might want, I don't know, how many of you remember the difference between resistance and resistivity? Some of you, but maybe some of you are confused. So imagine if I tell you that iron has this much resistance. What's the problem with that description? I'm telling you that iron has 100 ohm resistance. An ironware or iron-based, rectangular material has 100 ohm resistance. What's the problem with that description? Because yes, go ahead. Absolutely, you are right. Not just shape, but also the size and dimension. Any dimension changes will lead to a different resistance. So you'll have to ask me, hold on. What's the size? What's the length? What's the area? What's the shape of the iron object that you're talking about? So that's an incomplete information. But if I tell you the resistivity of iron is so and so, so I'm giving you this number, which is a material level, parameter. Once you know this, if it is a simple shape like this, you could multiply it with length and area cross-section and divide it with cross-sectional area to calculate the resistance. So resistivity is a more fundamental, not really fun, like a deeper level parameter than resistance. All right. So it's easy enough for us. If it were a cylinder, we could have calculated this, cross-sectional area of the cylinder and multiplied with that area. That's okay. Not much difference there. So it's easy enough for the, metallic entities. But for semiconductors, it's a little bit strange, and I'll show you that in a second. But let's go through a couple of steps first, even for the simple metal. Current density is current per unit area, as I just told you. What is electric field? Voltage over length. So imagine if you have a voltage V between 2 points which are d distance apart, the electric field would be V over D. Okay, very simple concept. So you have electric field and you have current density. Apparently, Ohm's law should be written, as I told you in the last class, not in form of V equals IR. More fundamentally, it should be written as, so let's go from V equals IR. Let me write it in a way that you have 1 over R times V. What is inverse of resistance? Conductance. All right. So remember, this is conductance. So instead of writing current, I should have written current density. Instead of dealing with voltage, I should have dealt with electric field. All right. Instead of dealing with conductivity, instead of resistance or conductance, I should have dealt with a more fundamental constant like conductivity. Yeah, like resistance, resistivity, conductance, conductivity. So conductivity is like more fundamental material level parameter. Okay, this is J equals sigma E is a more fundamental version of Ohm's law that we should be using, by the way. All right. Okay, so let's get back to this one, the previous slide. So this is J, as you see, I over A is just J. Sigma is conductance, and V over L is just AE. So you are basically writing the Ohm's law here. I guess all with me so far? Okay. So basically it's showing, this is taken from textbook again. It's showing that basically we should arrive at V equals IR starting from J equals sigma E, not the other way around. J equals sigma is the actual version of Ohm's law. Now, why did we talk about all of this? This is simple enough. Let's now go to semiconductors and use the same argument to find the conductance or conductivity from there. So this is J. You just saw using the drift current equation in the previous slide, right? In the previous slide that we used. J was something times electric field. So that's something, let's go here. J equals something times electric field. So that something has to be sigma, don't you think? Comparing that with Ohm's law, J equals sigma E. So when you compare that J with this J and this electric field with that electric field, whatever remains would be sigma. Does that make sense to you or not? All right. So conductivity. Sigma is the conductivity of. Are you guys all with me so far? So can I write that this is sigma? If this is sigma, mu n plus mu p, p. Resistivity will be just opposite of, I think I wrote it here. 1 over R is conductance. So if you take 1 over conductance, that will give you resistance. Okay. So if this is, let me just go back here. If this is sigma, which is conductivity, what will be resistivity? Basically the opposite, reciprocal. So this is your resistivity. So the resistivity of a semiconductor is like this. Or if you're okay with just representing it as conductivity, this is the parameter you should look at. Are you guys all with me so far? Now, here is the interesting fact. I mean, it doesn't sound like much, honestly. And I don't think, you're probably going to pay attention unless I tell you that this equation got engineers excited about semiconductors in the first place, because it shows you the resistivity or conductivity, whatever, like vice versa. I'm going to start using just one of them because they're the same thing, reciprocal, right? Say the resistivity of semiconductors can be controlled by doing what? By controlling the number of electrons and number of holes. And how can you control the number of electrons and number of holes? Anyone? By doping. If you want to increase the number of electrons, use more dopant. Number of holes, use more acceptors. So you could control these parameters, and in doing so, you can increase them, decrease them, and in doing so, dynamically change the resistivity. Does that make sense? For a metal, resistivity is a number. Take it or leave it. Done. Copper gives you that much resistivity. Rho. Done. Silver, another number. So if you don't like certain resistivity, move over to a different metal, or a different metal, or a different metal. Am I making sense, folks? Now, that's all good. Sure. I mean, if you need to create a certain resistivity, you can always make alloys. That's a difficult job to do, but it's okay. It can be done. You know what the challenge lies? The challenge lies in dynamic tuning. There is a difference between dynamically changing the resistivity, meaning while you are using a certain device, you have already made the device. You have already used a metal. Now, if you want to change the resistance, are you going to go and change the metal there in the device or the circuit? Is it possible in an integrated circuit? No. But imagine if you had a material whose resistivity could have changed over, during the usage time. Like while you're using it, by applying a voltage, if you could modulate the resistance, that would be fantastic. So far, what you have seen is resistivity of semiconductors is a function of the number of electrons and holes in it. And the number of electrons and holes could be changed by changing the doping concentration, which is similar to changing a metal as well, because you're doping it during the fabrication process. But what you haven't seen yet, and you'll start seeing gradually when you start talking about devices, it's possible to change the number of electrons and holes within the same material by applying voltage, certain voltage, or applying external stimulus. So you haven't seen non-equilibrium yet. That's where we begin today, by the way. So far you have been seeing thermal equilibrium. Whatever electron is being generated is either being generated by the donors and acceptors or by thermionic process. But you haven't seen what voltage can do, okay? So that's a very interesting thing about semiconductors. So keeping that in mind, let's move on to the next slide. Oh, by the way, there is one other simple line here. If it is an intrinsic semiconductor, the number of electrons and number of holes were all Ni, as we have talked about many times. And basically, this is the intrinsic conductivity. Simple. These are all taken from book. And by the way, I basically covered like a couple of pages of textbook here in this simple slide. All right. Now, let's move over to the next one. This is the graph that I've been, kind of talking about. Even in the last class, I told you that at some point you'll see, this is the velocity versus electric field, by the way. Velocity versus electric field. And we started talking about how it is a linear function. It should be a linear function ideally. But it actually saturates at a certain point. At a certain point, it will saturate. So you can no longer use this argument of V equals mu E. It's no longer a linear graph. It will saturate. So now what do? You have to make it a little bit more complicated. And this is also an empirical expression, by the way. This is also an empirical expression. Using this type of formulation, you could potentially fit a curve that will somehow represent that characteristics. Okay, I'll explain why that happens. This phenomena is known as velocity saturation. So as you keep increasing the electric field in a semiconductor, electrons or holes, or in general carriers, they start moving faster and faster, driven by the electric field. But at some point, their velocity no longer increases. Okay, how many of you have heard about particle accelerators? Great. You know where the biggest particle accelerator in the world is? CERN. Yeah, thank you. You're right. It's in Europe. So multiple countries. So I don't want to name one country, but yeah, that's the biggest particle accelerators. What do? They basically, as the name suggests, accelerate particle. What do they use to accelerate particles? Magnetic field and electric field, basically. You use magnetic field to make sure that the particle doesn't collide with the walls. It's literally kind of floating in a vacuum. And then you use electric field to kick it around in one direction so that it just keeps moving. So what am I getting at? You can increase the velocity to basically an indefinite level by applying more and more and more energy, electrical energy, through electrical field. The question is, why don't we talk about velocity saturation? If it saturates, how can we accelerate, right? It's literally staying the same with all those additional electric field. No, it will not saturate in vacuum. Remember, the more electric field you provide, the more velocity you get. The concept of velocity saturation is only applicable for electrons that are inside a material. And that's what we care about in electronics, by the way. It's not particle accelerator, where you can accelerate it to theoretically arbitrary velocity. But here, you are stuck with a moderate velocity. It's like not really that much, 10 raised to 6, around 10 raised to 6. centimeter per second. All right. Why is that? Can anybody tell me why we have to worry about saturating velocity in materials? Doesn't not necessarily in semiconductor only, in any material that has a crystal. Electrons will saturate. They cannot arbitrarily be accelerated, no matter how high the electric field is. You see, we're basically providing orders of magnitude electric fields. We're not just making it double. We are changing an order or multiple orders, but it's still not doing anything. The velocity remains the same, unlike in a particle accelerator. Why is it so? Can anybody guess? Yes? Thank you for trying. That's not the reason. I'll counter that argument. For example, in a particle accelerator, we could do just fine. We could increase it even further. Yes, we cannot go beyond 3 raised to say some value, 3 into 10 raised to 8 meter per second. This is in centimeter, by the way. So we are farther out from the speed of light as of now. But still, even if we approach that, we could definitely go beyond this limit, by the way. Maybe not the speed of light, but close to the speed of light. That's okay, for example. But here, we cannot even think of going that high. We stop at much, much less velocity. Anyone else wants to try? And by the way, all these graphs that you see today in this lecture, in a slide, simple, not so interesting slide, was a problem, engineering problem for engineers a few decades ago. They were sitting in a meeting room with all these scientists, talking about, why is it happening, man? Right? And they didn't have any answer. Now I have an answer for you, because somebody did the experiment, they proved it, they did some math, they did some engineering, and now they can control it. They know why it happens and when will it happen. But at the time, it was an engineering challenge. So this is great. You don't necessarily need to give me the right answer, but please at least think about it in your mind, because that's what you need to do in your real life. In your real life, when you join an engineering firm or like a company, say, they're not going to ask you to take this exam every day. You go to the office every day and take an exam. Is that right? Midterm, final, quiz. Like, will your boss give you a quiz? Go ahead. I got 10 out of 10. No, that's not how you do real life stuff, right? You just go to your office. If there is a problem, you try to solve it. You don't solve it alone. You solve it in a team, obviously. But somebody might have a solution, not everybody. Nobody knows who will have a solution, right? So you have to practice thinking. So if you imagine, if you are in a company, you are a passive engineer, you never participate in discussion, you will never solve any problem, or never even counter argument with anything. So will you be useful for the company, right? Remember, you don't necessarily need to solve a problem. You might, but you should be able to comment on other people's suggestion. If a colleague of yours suggests that maybe this is how we solve the problem, based on your understanding, you said, no, this will not work because of so and so reason. That's also a contribution, by the way, because otherwise the company would have tried that and failed. You saved the company from trying the wrong thing. Making sense? So all of these are important. This is not this one, maybe this is solved, but there are many other things that you'll encounter in your career that I don't even know about, right? You'll figure out the answers for it, by the way. Anyways, so imagine you are trying to make the fastest MOSFET, or you don't even know MOSFET, I guess, transistor, say, fastest device. You make it, the faster the electrons flow, the faster the device is, by the way. So you want to make it fast, but it's not doing its job. You're trying to increase the voltage, but nothing's happening. Why? Who is the culprit here? They realized velocity saturation. And we'll get back to this concept in the MOSFET lecture as well. That led to basically paradigm shifting decision in device design, when people discovered that velocity saturates in a semiconductor. And I'll tell you the simple reason. The simple reason for saturation is interaction with crystal atom, like interaction with atoms in a crystal. So in a silicon atom, for example, silicon crystalline, for example, atoms are everywhere. When electron is moving through them, and the same simple concept will come back over and over again. Sorry, I meant to, it's not letting me clear it, but that's okay. So the electron will interact. So the higher the speed is, the more interaction, the more scattering will occur, okay? So there is a certain separation in atoms in a specific crystal. And the velocity, maximum velocity that you can reach is kind of determined by the separation of the atoms in a crystal. So if the atoms are further separated from each other, chances are the electrons will have a higher velocity because they will scatter, but they will still have some time to speed up. Imagine in a race, right? If there are too many turns, the cars will have to slow down, don't you think? Can they arbitrarily speed up and then still stay on track? No. The moment you have to slow down and you're trying to accelerate again, and you bump into something else again, and you slow down. So apparently, there is always going to be a higher limit of velocity that they can achieve. Am I making sense? Who is making the electron speed up? The electric field. Every time they slow down after a collision, electric field again tries to accelerate the electrons, and they start running again, and they collide again. So there will be too many collisions. Are you guys all with me so far? So that's the reason why there is a saturation. So if you could have these electrons move in a vacuum, okay, in theory, you could have had indefinite velocity. Obviously, there is a universal limit, speed of light, but theoretically, you could accelerate it to a much higher velocity, but you cannot in a crystal. Okay, as an engineer, what does that tell you? Let's try to create a device that has a chamber, which is nothing but vacuum. Okay, so if you're curious, I just wanted to take this tangent. Just Google vacuum channel transistor. So NASA uses it, by the way. NASA came up with this idea and they use it. Basically, they did exactly that. Who is the limiting factor for velocity? Okay, material. So let's just completely get out of material in the channel where the electrons are flowing and create a vacuum channel transistor. And there you go. Solve the issue with. There are other ways to solve it, but anyways, let's get back to the actual course. So this line, this blue line, shows the velocity saturation curve for electrons, and the other one shows the velocity saturation curve for holes. So apparently, electrons saturate. Let me go back here. Electrons saturate at a certain electric field, and holes saturate at a different electric field. So there is a difference. You notice that? So if you dope a semiconductor with N-type materials, you'll have an abundance of electrons. And when you apply an electric field, electrons will flow, but there will be an upper limit of velocity. Okay? And that upper limit will be reached at a certain electric field. And by the way, electric field is basically interchangeable with voltage. So the velocity of electrons will saturate at a lower voltage, say. But velocity of holes will saturate at a different voltage. But they will all saturate at some point. That's the point. That's the important thing. All right. So you cannot, this equation that you saw, this is only an approximation up to what? Up to the saturation point. And beyond the saturation point, this no longer holds because you are assuming this will keep going on. That will not happen. Am I making sense? Okay. So then what do you have to do? You have to use a more complicated equation, and this equation will look a little bit more complicated, but doesn't matter. You get the idea. All right. And again, these are empirical equations. These are not physically derived. You use more like a fitting curve to kind of somehow fit into it. Because there is not one phenomena that gives rise to this saturation. Like I said, these are all random scattering events. You cannot really predict. Every electron will scatter in a different way. So you cannot just have one physical equation describing this. All right, I'll move on to a different concept now because I guess you are drifting away with the concept of drift right now. So I guess like things are getting a little bit boring. So let's get back to a different one, different topic. That's diffusion, carrier diffusion. Sounds really benign, like uninteresting, unimportant problem or concept to talk about. But did I tell you in the last class that these two types of current, drift current and diffusion current, will govern the properties of almost all of the devices that we'll learn about? Interesting. So in electronics, in chip design, all we do is find ways, interesting ways to control drift and control diffusion. That's all. That's how you control current. Control drift, control diffusion. Okay, so I mean, it doesn't have to be super exciting or interesting to be of use, to be useful. All right. So notice this is electron concentration. I would like to start with a graph here. This is distance. Imagine you are in a certain space where electron concentration is more here and less here. Somehow, doesn't need to be an electronic device. In any space, You have more electrons here, less electrons there. What does your intuition tell you? What will happen if you have more of something and less of something else in terms of particles? Typically, the particles diffuse, and we basically use the term diffusion, diffuse from high concentration zone to low concentration zone, right? So apparently, these electrons will flow from always from high concentration to low concentration. All right. Any problems so far? One other thing. How about holes? Imagine you have somehow managed, I haven't even told you how, you have somehow managed to create higher concentration of holes here and lower concentration here. What will happen then? Same thing. The holes will diffuse in the same direction. Any problems so far, folks? Okay. Now, just to highlight, holes are positively charged particles. So I'm going to write H plus, and here I'm going to write E minus, so that you remember. When the electrons flow in one direction, where will the current flow? To the right, the electron current. But when the holes flow in certain direction, maybe here, where will the current flow? Same direction. So this is hole current. So you notice that if you create a, what we call density gradient, difference in density or density gradient of the same type. So you have more in one side, less in the other. For two different carrier types, the current originating from these two carriers will be in different directions. Does that make sense to all of you? Okay. So apparently, they will oppose each other. So the electron current originating through diffusion will be opposite to the whole diffusion. In electronic devices, we engineer ways, folks, honestly, I know this doesn't sound exciting. This is how people start thinking about new devices. Here is what you need. We need to create more density here, less density there, so that current will flow here. So let's go back and use different heterojunctions, different materials to create a phenomena that will lead to pile up of electrons here and less electron concentration somewhere else. In a p-n junction, I mean, just to make it a little bit meaningful, n-type, p-type. In a p-n junction, you have more electrons in the n-type region and more holes in the p-type region. Okay, so what we try to do is when you apply voltage, say negative voltage here, you try to push some electrons over to the other edge. So you have electrons here now. Notice you have more electrons here and almost zero electrons there. What happens then? You just have to push it to the other side and electrons will diffuse. Am I making sense? Basically, that's how we design it. That's how p-n junction is designed. Somehow push these electrons to the other side and diffusion will take care of the rest. Are we good? All right. Okay, so I just wanted to give you a link. We'll talk about it in greater detail in the other lectures. By the way, diffusion can be expressed. These are all interesting mathematical equation. I'm gonna be very brief about it now. Diffusion current density is related to the density gradient. By the way, density gradient is nothing but the slope of this graph, which is dn over dx. If I go back here using simple geometry, if you have y versus x, what is the slope of this graph? Can I say dy over dx? Simple calculus, right? Similarly, this is n versus x graph for electron, concentration versus distance graph for electron. This is concentration versus distance graph for holes. So I can say the gradient, this gradient will be dn over dx. And the diffusion current, the more gradient you have, the more current will flow, the faster it will diffuse. Okay, so sure. So diffusion current is related to, obviously, the gradient for both electrons and holes. And this is a constant. So if I write J is proportional to dn dx, you have to have a proportionality constant, right? To get rid of this proportional sign. And that constant, I mean, I could have used alpha, beta, gamma, doesn't matter. Engineers decided to use D. D stands for diffusion, as you see. Diffusion constant. N represents electron. Diffusion constant for electrons. Simple. And by the way, this is the number of charge. When you say if you have 100 charges, everyone has the charge of an electron. What is the total charge? 100 times the charge of an electron, don't you think? So similarly, multiply the number of charges with the charge of electron, you get the total current density. Simple. So same thing applies to the holes, because holes have the same charge as an electron, just the opposite type, that's okay. The only difference there would be you're dealing with gradient of hole concentration instead of gradient of electron concentration. The other thing is, instead of diffusion coefficient for electron, you're dealing with diffusion coefficient for holes here. Okay. One other subtle difference is that you just noticed, if you start with the same type of gradient, you'll have opposite kind of current. So if one is positive, the other one will be negative. Are you guys all good? You have just seen that, okay? All right. So keeping all of this in mind, in one semiconductor where you have both, you have an external electric field, you also have a density gradient. You have both. We started with no gradient, just electric field, so drift. Second phase, we completely obliterated the electric field, just had a gradient, we saw diffusion. Now imagine if you have both, you have drift and diffusion both, right? So then this is the total current in any semiconductor device that you can ever think of. This covers everything, okay? You have drift current due to electrons, drift current due to holes, diffusion current due to electrons, diffusion current due to holes. Okay, does that make sense? And notice everything is additive except for the diffusion side. They will be opposite to each other. If one is positive, the other one will be negative. Simple, right? So depends on which direction are you going to take as positive, depends on what you're doing for drift. Simple. So typically this is how we represent it. We, provide more emphasis to the electron current. That's easy to measure and represent. And we use negative sign for the whole current. That's all. It's just a convention. Okay. Now, what is the difference between this and the other equation, folks? So far, when I use dN over dx, what does that tell you? Why just x? Why not y? Why not z? Because when things diffuse, they don't diffuse in a line. They diffuse in a space, in a volume, right? Does that make sense to you guys? So instead of using dN over dx, I should have used dN over dx plus dN over dy plus dN over dz. So basically in 3 dimensions, right? How many of you remember what this operator represents? Basically, we just represent it with divergence, right? Simple. So in 3 dimensions, you could either write it up, spell it up as dN over dx, y, z, if you want, or you could use this simple operator to represent 3 dimensions. Any problem so far, folks? Drift, well, that didn't matter too much because we didn't have any XYZ components there. Electric field is applied in one direction, things go in that direction. Simple for drift. For diffusion, it is 3D. So you have to think about derivatives in all dimensions. All right. Finally, see, there is a line in red here. There is a sentence in red. You can read it, but I'm going to tell you in the next slide. Turned out, scientists realized that diffusion coefficient and drift coefficient, they're not independent. It feels like they're completely different phenomena. Drift is driven by electric field. Diffusion is just driven by density gradient. But turns out the coefficient that shows up in the drift equation and diffusion equation, they are correlated. And the proof of this equation is also there in the Niemann's book. If you want, you can see it. Super easy. But still, I'm trying to reduce as many tangents as possible. So I'm going to show you this equation. This is known as Einstein's relation, by the way. So obviously, should pay attention. Einstein did a lot of things, obviously, in addition to E equals mc squared. But this simple equation has a lot of implication, by the way. It shows that drift and diffusions, they're seemingly 2 different phenomena, but they have some link, some physical connection as well. So this is drift coefficient for electron, diffusion coefficient for, let me rephrase that. Diffusion coefficient for electrons and mobility for electron, right? Mu(n), we gave it a name, mobility constant. Because drift is related to mobility. How mobile are they? Similarly, diffusion coefficient for holes and mobility for holes. The ratio of the two is always kT over E. Do you guys remember I showed you this term before in a different context. I told you this is the thermal voltage, right? If you have temperature T somewhere, that will create a thermal noise, which is kT over Q. Q or E, that's the charge of an electron. So apparently this constants, the ratio of these constants, interestingly, is nothing but the thermal voltage. So there is something fundamental about these two phenomena, all right? So we don't want to divert too much, but remember, if you know one of them, you can calculate the other using this simple equation. And this is often given in your exams, mu n and mu p, dp and dn for different materials. They're all experimentally measured. Okay. All right, that concludes this lecture, and I'm going to stop and see whether there are any questions. I expect one question, and I got that question just once. Okay, let's see if anybody has any questions. No? All right. I'm going to ask that question anyways. And maybe I'll not give you the answer. I'll see whether you can figure out the answer. Okay. So you guys have been seeing in your life that things diffuse. If you have more concentrations of, say, a material somewhere, it diffuses. So if you spray a bottle of perfume somewhere, after a while, the entire room will smell like the perfume, right? That's diffusion, a very simple way. But why do you think, how do they decide that we need to diffuse? Say 10 friends, like maybe 10 of your friends, they're chatting with each other in one corner of the room. Will they have to diffuse around the room naturally? If they don't want to, they can always stay there. They don't need to diffuse, do they? It's not like, oh, there are 10 of us, one of them, so we need to diffuse. That's not how it works, right? And particles don't have their minds like that. Okay, let's diffuse. Why do they always diffuse? And it's so fundamental that even carriers, when you have a concentration of electrons somewhere and less concentration somewhere else, even the electrons diffuse. When we talk about perfumes, these are the atoms. Electrons are much, much smaller, as you can see. Even they diffuse in a material. My question is, why? What you have to somehow connect it to a more fundamental reason. More fundamental. Okay, they've diffused. Sure, I could just stop there. Have you ever asked that question to? Yes, please go ahead. Higher entropy state? Perfect, man. I'm really pleasantly surprised. Thank you so much. Yeah, I'm really happy that you know that. How many of you know about entropy? Almost all of you have heard about it, right? Okay. So instead of entropy, we could also connect it to energy, but it is essentially entropy, by the way, right? The world is heading towards lower or higher entropy. Do you remember? The universe. So typically, we are trying to lower entropy. Basically, entropy is a measure of chaos. Okay, everything tries to settle down. Higher entropy represents higher chaos. Okay, if the more chaos in a system, the more usable the energy is. Again, I don't want to digress it too much, take it into physics. The point is, gradually, if things settle down, entropy reduces, and the entropy in the universe is actually heading towards zero gradually. Then everything is settling down. So when you have more electrons piled up together, they have higher entropy, and they try to reduce entropy. That's the nature of the universe. And in doing so, they have to move away from each other. But if you move away from the concept of entropy and just think about energy, when electrons are piled up together, they're all negative charges. They can interact with each other, and they repel each other. There is more energy. Making sense? There is more interaction and more energy. So if they move away, there will be much less interaction and much less energy in the overall system. Am I making sense? So apparently, that's what they do. That's why they diffuse. There is a fundamental reason. It's not like, okay, maybe we'll diffuse today. Maybe we'll not. But thank you so much for the answer, by the way. I'm really happy. Okay, all right. So let's move on to the next one. Next lecture. And finally, we are seeing the term non-equilibrium. See, equilibrium is over. And I told you the previous lecture was like an interface lecture. They're getting you ready for non-equilibrium. We'll start seeing what happens when you disturb a system with external stimulus. And the next lecture, surprise, surprise, after this lecture, non-equilibrium carrier concentration, will be p-n junction, right? The first device, electronic device that we'll learn about. And after p-n junction, you'll learn about BJT and MOSFET. So gradually, things will increase in complexity. So you're looking at a few terms here. Non-equilibrium, excess carriers in semiconductors. First of all, what is non-equilibrium? You guys must remember what equilibrium is. When you don't provide any external voltage or current, or a light or magnetic field or thermal gradient, no external stimulus, that means it's equilibrium, thermal equilibrium otherwise. That means if you bring in any of these external, energy sources to a system, that's non-equilibrium. Obviously, for electronics, we will eventually care about electrical stimulus. Like when you apply a voltage, that's all that matters for electronics. But in principle, there are photonic devices. There are optoelectronic devices where even light stimulus matters, by the way. Okay? So magnetic field, there are magnetic devices as well where magnetic field could change some things. That also will fall under the same category. Now, when there is an external stimulus, when there is a non-equilibrium, you have to think about two concepts: generation and recombination. And I'll talk about that. And I start with this boring slide because this is taken from the textbook, as you see. And textbook wanted to set the symbols first so that you don't get lost into all those equations. What is N0? What is Ni? What is blah, 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 right? And don't look at the term. Just listen to me. When anything has 0 in it, it represents thermal equilibrium. Okay? N0 represents electron concentration, thermal equilibrium, at thermal equilibrium. P0 represents electron concentration at thermal equilibrium. Okay. What is N and P without any subscript? They represent total electron concentration, and P represents total hole concentration. What do I mean by total? When you disturb a system with external stimulus, there will be some excess carrier concentration. You see, I'm using the term excess, and that was in the title as well. You see, excess carrier. So there will be, any non-equilibrium system will always have equilibrium carriers as well. In equilibrium, you still have carriers generated because of temperature, right? So they will also be there, but then there will be some excess carrier on top of the existing carriers. So what you learned so far will be valid, will already be there. And then on top of it, you have something extra. And that extra will be represented with delta. Delta N, delta P. So excess electrons, excess holes. So what will N be? Total electron will be whatever you had during thermal equilibrium plus whatever you are generating as excess. Similarly, what is the total number of holes? Whatever you had during thermal equilibrium and whatever you generate as excess carrier. Am I making sense, folks? So you can generate excess carriers through external stimulus, but thermal equilibrium stuff will also be there. How many of you remember? How can I create thermal equilibrium electrons and thermal equilibrium holes? There are two mechanisms. One, I don't do anything. Temperature does it. So because of external temperature, spontaneously, some electrons will go from valence to conduction band. There will be a hole and electron pair generated. That was one. What was the other? Doping. Are you guys still with me? So when you dope a semiconductor, that dopant level will create some electrons in the conduction band or valence band, depending on how the doping is. Is it N-type doping or P-type doping? Remember, those electrons and holes were not generated in pairs. You either create electrons or create holes using doping. Don't forget that. All of those concepts, they're all piled inside this one, N0 and P0. What you have as delta, that's something else. That's what you get when you inject light or apply voltage or do something to the semiconductor externally. So that's all comes into delta. So whatever you've learned, they will all be within N0 and P0. So we have covered this, we've covered delta N, delta P. You see, we covered four lines. What's left now? Remember, G stands for generation. R stands for recombination. So when you generate carriers, sure, it's generation. Carriers can also, when I say carrier, it's electrons and holes. When electrons and holes meet each other, they can recombine. They can basically cancel each other. Okay, and this is basically visualizing, like, imagine an electron decided to go from valence band to conduction band. So you have an electron and hole now. After a while, the electron comes back. It loses energy and comes back to the valence band. What does that represent? That represents that electron will now nullify the hole. Basically, there will be no more void space, a space devoid of electron. That means one electron will recombine with one hole, and completely destroy each other. This is recombination. Making sense? Okay, so when I say GN, that's generation rate. Generation rate, and typically in textbooks they will use a prime here just to represent it's a derivative. Rate, derivative with respect to time, DDT. Okay, so just to represent that, they use generation rate for electron, generation rate for hole, and that covers this line. Are you guys all with me so far? And remember, now we only care about the excess electron generation and excess hole generation, not the ones that were generated during thermal equilibrium. Are you guys all with me? So when you, I mean, I don't have the others here, but in the textbook, they sometimes use capital G or uppercase G. That represents the whatever was generated during thermal equilibrium and whatever is being generated with external stimulus. So together, like this concept, right? Whatever you had before, whatever you have generated now. Simple. But for the most part, we'll be dealing with this lowercase g because we are dealing with excess carriers here. So Gn, Gp. I hope you are not going to be confused by this. Generation of electron, rate of generation of electron, rate of generation of hole. Just to represent it's a rate, we're going to use prime. Similarly, recombination for electron, recombination for hole. And since this is a rate of recombination, we're going to use prime. So that covers the other line as well. Finally, and this is also marked here, this is very important, tau. This is known as minority carrier lifetime. Minority, I'll explain why minority carrier lifetime. Imagine if I write tau n, n represents electron, p represents hole. I'm going to say this is the lifetime of electron. So what does lifetime mean? Once you create an electron, it will be there free, moving around for a certain amount of time. After a while, it will recombine and will be out of picture. So there is a time difference between generation and recombination. If you generate, after a while, it will recombine. Done. It's gone. Okay. You might be wondering, okay, so how do our devices work? If you generate and things recombine, then it's gone. That means you have to create a process that will continuously keep generating. Right? Am I making sense? All right. So can I take a simple tangent for 10 seconds? How many of you heard about solar cells? All of you, right? The biggest challenge in solar cell that engineers try to tackle is how to separate generation and recombination. So when you shed light, non-equilibrium. Okay? Solar cell is nothing but a p-n junction. Simple. You have p-type and n-type semiconductor side by side. When light comes, it generates carrier, extra carrier, electrons and holes created. If you could somehow separate them out before they recombine and destroy each other, there you go. You charge up the battery. But if you don't, if you set a solar cell and light comes in, it will keep creating electrons and holes forever, but you cannot charge anything because after a certain amount of time, it will recombine and cancel each other out. Are we good? So this is a part of engineering. How do you stop recombination? How do you basically, before they recombine, how do you separate out the electrons? If you could separate out at least one of them, the holes or the electrons, if you maybe use a positive charge zone that will attract the electrons. So rather than trying to fight with the holes again, they will come back and get to the positive side and they will be out of the picture. So no question about recombination. Am I making sense? That's basically part of the challenge. So that, yeah, if you don't do anything else, excess carriers will be created, generation, and they will recombine, go out of picture, recombination. We know that this is the case. But to make them useful, you have to. So this time constant, I mean, why did I take that tangent? Okay. It's very difficult to sell, by the way. These things are very difficult to sell because they are not like drones flying around. See, it's flying. But they're connected to more fundamental things that we can realize. So if you have a material, just imagine for a second, if you have a material in a solar cell that has a higher or larger, longer time lifetime for carriers, meaning what is lifetime? Time difference between generation and recombination. How long it takes to get recombined and go out of picture, right? A nanosecond, 10 nanosecond, 20 nanosecond. If you have a material that has a longer time frame, that gives you more time to separate out or filter out the electrons and holes. So if you have a material that, imagine light comes in, you have sea of electrons created, super awesome material, amazing. So you have a lot of electrons created, but then the lifetime is slow. Okay. So people deal with this type of dilemma in solar cell design, like which material will create most electrons when you shed the same light, right? Okay, this material creates most electrons, but how about the lifetime? So you have to design a process which will filter them out within tau. So this tau n and tau p are important parameters. Anyways, getting back to our stuff. What is tau n? Lifetime for electrons. Tau p, lifetime for holes. By the way, I'm going to use another term here. Not just electron, I'm going to use minority electrons. Remember that. And I will get back to this comment before. Lifetime of minority carrier electrons. Lifetime of minority carrier holes. So here is what it means. Imagine if you have a material which is N-type silicon. N-type silicon, okay? In this material, I will care about tau p, which is because N-type material has more electrons, as you can imagine, but it will also have holes. I explained that before because of during thermal equilibrium, electrons and holes are always created in pairs. So there will be some holes even in N-type materials. Do you guys all remember that? There is another way to remember. You can never have 0 holes in an N-type material. Why is that? Can anybody tell me? You can never have absolutely 0 holes, no matter how hard you try. How many of you remember NP equals Ni squared? I told you, this is what the semiconductor, maintains. The number of electrons and number of holes will always be equals to Ni squared. Imagine if you have absolutely 0 holes, like P equals 0. What will be the number of electrons then? Infinity. The only way you could have no holes in the system will be if you have infinite number of electrons, which is impractical. So you can never practically, any questions? So you can never practically have 0. Vice versa, that goes either ways, right? You can never completely diminish one type of carrier. That's another interesting thing, which we basically overlook. Well, NP equals N squared, who cares? But that enforces that there will always be some carriers that are minority. There will be in small numbers. But if you in an N-type material, if you increase the number of electrons, the number of holes will obviously go down because the total number, product of total number will have to be constant, Ni squared. Okay, all we do by doping, we create abundance of one type and less of the other type. Now, having that in mind, in an N-type material, who is minority carrier? Folks, tell me. Holes. So in an N-type material, we'll care about the lifetime of holes. Minority. Interesting, isn't it? It's an N-type material. All actions should be driven by electrons because, it's N-type. Makes sense. But turns out the lifetime of excess carriers, the carriers that are created, through external stimulus, is controlled by the minority carrier lifetime, not the majority carrier lifetime. Now, we'll get back to this towards the end of this lecture. Okay, just keep that in mind. Counterintuitive, by the way. If you have a p-type semiconductor, you have an abundance of what? Electrons or holes? P-type. Holes. But who will be minority carrier there? Electrons. So we should care about tau n, lifetime of electrons that are minority carrier in this semiconductor. That's what I'm telling you. So tau n and tau p represents excess minority carrier electron and hole lifetimes. So imagine when I first read it, what? And this is in the first page of the textbook, right? As a student, just imagine. This is super confusing. Why minority? Why this and that? Anyways, and typically they use a 0 with both of them for no reason. They always apply to excess carriers anyways, but for no reason they just always apply to 0. All right, now let's get to the next slide. Carrier generation and recombination in equilibrium. So we are taking a step back and looking at what happens in thermal equilibrium. In the next slide, you'll see what happens in non-equilibrium, right? So the difference. So in an equilibrium, we have talked about it many times. When an electron gets some energy, somehow externally, it goes up to the conduction band and creates an electron hole pair. And if you have 10 electrons, you have 10 holes. So basically, the generation rate for electron will be equal to the generation rate for holes. You guys all agree? Super simple. Generation rate for electrons at thermal equilibrium will be equal to generation rate for holes at thermal equilibrium. Simple. And by the way, let's see what happens when they recombine. Imagine an electron moving around. After a while, it basically merges with a hole. So, and I told you that simply because I draw an electron here in ECE doesn't mean it's physically in a different location, right? It is only representing the energy. They could be in the same space, but have more energy and less energy. So it doesn't represent the space. But imagine when that electron is flowing around the crystal. This is not the right way to draw it. It's not flowing around here, basically. I mean, in the crystal. And it encounters a zone where there's a hole, and hole means one less electron. It could easily, fill the void. And that means the hole will be out of picture, and the electron that was free will no longer be free. They don't visualize it in a way that, because some people do, that electron is getting destroyed. There is no destruction here, by the way. There's a void of electron, which is a hole. And that electron just felt like, oh, you need an electron? Oh, sure, I have, yeah, sure. I can help. So that electron will go and fill that void, and it will be stuck there. It will no longer be free. That's the reason. We are talking about free electrons not being there, not electrons not being there. Electrons will be there. Am I making sense? Okay, so that electron can potentially recombine, we are using the term recombine here, with a hole and basically go out of the picture. And then the recombination rate, as you see in equilibrium, also happens in pair. So if you lose 10 electrons, you'll also lose 10 holes, because they will basically interact with each other and recombine. So the recombination rate at thermal equilibrium is also equal. So apparently, in thermal equilibrium, overall generation rate and recombination rate, they are all equal. Their carriers are generated and they recombine. Generated and recombine. So if you just keep a material, don't apply any external stimulus, nothing interesting will occur. There will be some random carriers generated, and they will also recombine and go away. Nothing interesting. Okay. Now here, let's see what happens when you have excess carriers. And we'll be using an easy example here, the example of shedding light. H mu represents light. So light is coming to a semiconductor. In this zone, notice I've written N0. If you forget the zone on the left and just look at the zone on the right, that should be, easy enough for us to understand based on our discussions in the last class. Why do you see more electrons in the conduction band than holes? Who can tell me? Why do you see more electrons in the conduction band than holes? Because this was a N-type material. So I somehow doped it with, N-type dopant, and that created more electrons. So there, remember, pairs of electrons and holes are created for thermionic reasons, like this. But why do you still have extra electrons? Because you doped it N-type. So there are some extra electrons coming out of the dopant, by the way. Okay. So either ways, the total electrons was here, and there are some holes as well in the system. We are not talking about any of them. They will be there for sure. They're not gone. They're here. But what happens when you apply an external stimulus? Let's see what happens there now. This light will excite some electrons from the valence band and take them to the conduction band. So it will again create pairs of electrons and holes. Surprise. So external stimulus also creates electron and hole in pairs. Like 3, 3, 10, 10. Right? Isn't that interesting? So external stimulus will also create the same number of electrons and holes. But when these electrons add up with the rest, the overall number will change, as you can see. It will still be predominant electrons and a few holes. But if you only consider the excess portion, they will be created in pairs. Are you guys all with me so far, folks? All right, we're getting there. No worries. Let's see how the recombination works. If you don't care about whatever was already there in the thermal equilibrium, these electrons that are being created could also, at some point, recombine with holes and basically go out of picture. And they will this is important. Let me highlight that. This is they can re-establish thermal equilibrium. So if you create non-equilibrium momentarily by shedding light, for example, this will not be a permanent process. This process will restore back to where? It will restore back to, notice, this was thermal equilibrium, and this is thermal equilibrium again. So after recombination, you will get back to thermal equilibrium. In a system, in a semiconductor, if you somehow create excess carriers in a system, the overall material will act in a way that it will always go back to thermal equilibrium structure. Am I making sense, folks? It will make these electrons that you created in excess recombine with the excess holes and go back. This is the nature of the materials. Okay, nobody wants to have excess carriers than whatever is available in thermal equilibrium. All right. Now, we will talk about, and remember this process, how long does it take to go from here to there? So you created excess carrier, electrons and holes. After a while, they will recombine and go back to thermal equilibrium. But there is a time between these two. How long does it take to get to thermal equilibrium after you have created an excess carrier? This is called dielectric relaxation time. So, but what do I mean by relaxation? Once you excite a semiconductor by external stimulus, it takes some time for the material to relax down and get back to the thermal equilibrium situation again. That is dielectric relaxation time. And that relaxation time, we'll talk about it, we'll calculate it. It's a material property. This is the end product, but we can go through some maths. We'll see. This is a very important property for a certain material and eventually a device, because we'll talk about it soon. But before moving on to the next slide, I want to cover this as well. Notice the recombination rate for a p-type semiconductor is, are you guys noticing this? Please notice as I'm marking. That will hopefully make it easier for you to understand later on, because otherwise, I don't have everything written down here. Otherwise, you'll have to go back and read the book, which, trust me, is not going to be fun. So anyways, so this is the recombination rate in a p-type semiconductor. In a p-type semiconductor, okay? So you are looking at excess electrons, number of excess electrons, times, so divided by the lifetime of the electron. That is the recombination rate. But in a p-type semiconductor, why are we talking about number of electrons and lifetime of electrons in a p-type semiconductor? Because in a p-type semiconductor, we have more holes, right? And as I hinted in the first slide, that if you have predominant electron in a system, for excess carriers, the minority carriers will determine the lifetime, and vice versa for the other type as well. And here is why. Imagine you have, say, 10,000 electrons. It's a majority electron material, and you have 100 holes. Imagine for a second, will 10,000, all these electrons want to recombine and just get done with it. I don't like to be an electron anymore. I don't like to be a free electron anymore. I've done enough. They want to go back and recombine and just live a happy life. But will they be able to, will all these 10,000 be able to go and recombine and get stuck in the crystal again? Where is the bottleneck? Yes, because if they are trying to recombine, they'll have to recombine with a hole. Right? They'll have to fill out the void, right? So if there are just 100 holes, they're limited. The rate, basically, what is a bottleneck? Imagine. This is a bottle. Sorry, I meant to draw it properly, but I'm trying to show you a bottleneck. So imagine there is some liquid and you're trying to pour it. Which part of the bottle will control the rate? It doesn't matter how big this section is, how wide this section is, the rate, like say volume per unit time, rate of pouring water will be governed by home, the bottleneck, the neck of the bottle, right? This is the bottleneck, the lower number. So similarly, yes, electrons can recombine. They want to go and get stuck in the crystal again. I mean, they don't want to move around. They're tired. But then who will control the recombination rate, the number of holes? Because you can have that many recombination at a time. Am I making any sense, folks? Okay. So if you have 10 holes, you can have at most 10 recombination event at a time. And after all this, okay, then what will happen? Imagine. Begs the question. Imagine you have 10 holes and 10,000 electrons, as I showed you. Maybe 10 of these electrons will go and recombine. So does that mean you have 0 holes and 9,000 blah, blah, blah electrons now? So that is violating this NP equals Ni square rule. That means the material will generate more holes naturally, right? Am I making sense? And so the process will go on. That's true. But the rate of recombination, the rate will be determined by home, the number of holes that you have. So the minority carrier will control the rate of recombination always, not the majority carrier. Does that make any sense to you guys? For any type of material, remember, minority carrier lifetime is the determining factor for recombination rate for both. Okay, so here we'll try to calculate the time constant, but maybe we could do it in the next class, obviously. It's going to take us a while to explain this. And then we'll do some math problem and move on to the next concept. So let's stop here today. I don't want to start and then stop in the middle. Thank you all.